I'm going to start by introducing myself, because most of you, I don't know you, and you don't know me. So I started my life over here in this little circle. That's Korea, South Korea. And then some of you were wondering what accent I had. I moved to Australia. That's where I grew up. And that's where I actually started my research career. So I started doing some work on structural optimization. I then am here now, but I spent last year at some of these places in the States. And I'm going to talk a little bit about the sort of things I've been doing over there. So I'm an aerospace engineer. People think this is what I do. And you can see me here at Jason Yudva Air and Space Museum in Washington, Dallas, seeing the discovery. But then I tell people I do structures and think, this is what I do. These things don't obviously fly. So, and you can see my patriotic Sydney Harbour Bridge making a little appearance here. So what do I actually do? Well, if I get wrong what I do, this is what happens. So this aircraft that you get on is safe, but this is the sort of thing that will happen if I don't calculate things well enough, and if I don't design things well enough, it'll actually break apart in the air, and you don't like that. So the common question then is that why the black box material is used to make up all of the aircraft. Why is that?
Heavy?
Yes, excellent. So it's heavy, and we've got limited power. So aircraft engineering is all about balancing the weight against the power. So if we can reduce the power, obviously fuel economy goes on. This is now a very critical stage in this era to get this right. Before I move on, I just want to show you that this is the sort of testing that today's aircraft goes through. You can see the wing bend as far as that. The aircraft we fly today or tomorrow is safe. So I do structural optimization. I think mentioned the word earlier, so it's not so scary now that I'm mentioning it. I develop methods to design the best performing structures using these three different disciplines. So I work very much at the interface, and when I use that sort of method, you can see the structure that is actually being optimized. So my computer algorithm is actually optimizing these structures where I'm hanging the weights over here and I'm just clamping it on the top. So you can see I'm using my mathematics to do these calculations. The reasons why this is difficult, there are lots of variables, and materials are either there or not there, as you saw. This is a 0-1 problems, and mathematicians don't like this sort of problem. So when I actually develop these sort of methods, and then I apply to some practical applications, which is what I'm going to show you. So this is a turbine disc. This particular element here is what I'm interested in. Apparently it looks like aliens, but this is actually apparently what a turbine disc looks like. And so look at this design, which is what we have now, and when we apply our topology structural optimization method I mentioned earlier, at 25 weight reduction, it looks slightly different, and you can see the weight, where the weight has come out. I also apply that to aircraft wings. So this is a typical aircraft wing that you fly in. If you can actually look inside, you can see the top and the bottom skin, and inside is this sort of orthogonal, this sort of components that are going at 90 degrees. When we actually optimize using the methods that I've been developing, then you can see that thickness in the top and the bottom skins are actually varying in sort of weird shapes, and it's sort of thinner as you go towards the tip. And what's really quite interesting is looking at the wing from the top, very different from the sort of design that we have now. So we have these sort of column-like structures. Looking at it cross-sectionally, you see that this sort of design is very different from the current design. If we actually look at the inside of Boeing 787, when it's not on fire, this is what it looks like. So you can see that there's actually not much aluminium. It's very much carbon fiber. You may have come across these things. And I'm going to introduce some of the work that I've been doing using composites. And in particular, I want to introduce you to something slightly different. So we've got these piezoelectric patches which converts the mechanical energy to electrical energy. And we put that over the top of these composites. And then you can see that it's flapping back and forth quite madly. And as it's flapping back and forth madly, the electrical, the piezoelectric patch over the top of it is collecting that vibration into electricity. So I tell my students at the end of the talk, I must give a summary of what I talked about. So here it is. Thank you very much. And cheers.